All right, so today we were just going to finish up on the main topics of this course by finishing up on heaps. And then on Wednesday, we'll go ahead and give a short course retrospective. And then once everything is done on Wednesday, then there's no need for a lecture on Friday, so we won't be live streaming or lecturing on Friday. Instead, just like your lab this week, we'll use that time to go to help hours and get everything else done. At this point, you only really have assignment 8, which is all written, and your design document, your final draft to get in. So make sure that those are in by Friday. After you've got those in, then the course is done. There's nothing during finals week. There are no office hours during finals week or help hours or anything like that. All right? So keep that in mind. Anyway, what we were doing last time is we realized that Eric S. Raymond, smart data structures and dumb code are a lot better than the other way around. And that was exemplified with our application for a heap. One of them is a priority queue, but the other one was a heap sort, right? So here's our heap again. It's a min heap. And because of the properties of the min heap, it's always going to have order n or order log n operations to put stuff in and then to retrieve the minimum and then to replace it with something and then heapify it and fix it. So the idea of heap sort is that you can put stuff in and take stuff out. Let's go ahead and look at the pseudocode. We already wrote the actual code, but let's look at the pseudocode again. What I'm going to do is I'm going to initialize a new min heap. All right? And then for each element in the given input here, let's go ahead and label the input, is going to be A, which is A1 through AN, right? So for I running from 1 up to n, right, what we'll do is we'll say h dot insert or add or enqueue or whatever you want to do a sub I. There we go. So put stuff in, right? And then while h is not empty, take stuff out, right? So x here will be a, let's go with h dot get min. There we go. And then output, I don't know. Actually, let me go ahead and relabel this so that we'll end up relabeling A1 through AN here to be AI. And then what I'll do is I'll set I to be 1 and then I plus plus. There we go. Just to get it technically correct. All right. All you're doing is putting stuff in and then taking it out. You're letting the data structure, the smart data structure, do all of your work for you. And once you've done this, if you put stuff in and then you take it out and you're always taking the minimum every single time, then you're always taking 1, 5, what's next? 30, then 40, then 50, then 55, et cetera, et cetera, et cetera, or 53, excuse me, then 55, et cetera. You are sorting it, and that is called heap sort. So let's move all of this. Oops. Let's move all of this down and give it a name. Heap sort. And we observe that this is way better from a code perspective because all you're doing is putting stuff in and taking stuff out. It's way better than a quicksort, which is really clever code, no data structure at all. It's got this partition subroutine that puts things on one side or the other. And it's also got a pivot criteria that can be really complex. And then it does recursion, right? And so keeping track of that recursion and returning from that recursion and checking all those things, lots of moving parts there. Lots of really, really clever code. No data structure at all. This is only going to be good if it's better or at least as good as quicksort asymptotically. Like, is it as efficient, right? So what I want to do is I want to do an analysis, right? Analysis. How many operations or how many comparisons are done by heap sort in the worst case? So my first thought here is I'm going to go ahead and restrict my attention to, let's change this to blue or something, I don't know. Let's change our, restrict our attention to just this first phase right now, okay? Well, I'm doing it how many times? N times. And I'm doing this operation of insert, so if this is my elementary operation, then I'm only doing n and it's order n. Right? It's not that simple. This operation is actually doing stuff, right? It's doing stuff under the hood. In order to put something in, you of course need to find this last location, insert it, say I don't know, 54 or 45, let's say, right? And then you need to heapify it up. You are making comparisons and swaps along the way, okay? So remember that that the number of swaps on insert is order log n, where n is the number of elements in the heap H, okay? That actually changes. Think about the first iteration of this for loop. How big is your heap at that point? Have you put anything in it yet? No. So its size is 0. Then after the first iteration, then its size is 1, 2, 3, etc. It's growing. So what we're going to do is we're going to do what's called an amortized analysis. We're going to look at this with a fine-tooth comb here, and we're going to say, okay, each iteration is different, right? Because n is changing. This is not the same n as this n up here. This n is a different n. That's the size of the heap as it changes in this for loop, okay? So let's come over here and outline this. Let's think about each iteration. The iterations run from 1, 2, 3, 4, all the way up to n. In fact, let's go ahead and put something in between here, I, and then up to n. Right? And let's keep track of the size of the heap. Size of the heap. Well, on the first iteration, we've already observed that the size of the heap is 0. So consequently, what are the number of operations, the number of comparisons?
1.
Careful. Do you need to make any comparisons when the heap is null? You just make a new root. So technically, it's going to be 0 because you're not comparing it to anything. There's nothing to compare it to. Right? Now, on the second iteration here, what's the size of the heap? Well, previous iteration, you put something in it. So now the size is 1. How many comparisons do you make here in order to determine that it's where it needs to be, or you need to exchange it with that with that root you had? Just 1. Right? You could get away with 0 swaps, right? So we're not going to look at this with respect to swaps. On the third iteration, the size of your heap is 2. Right? So it looks kind of like this. Right? And if you insert something right here, then you will need to compare it with the root node. In other words, you only do 1 more comparison. Right? So it's not strictly going up each and every single time. Why? Because generally, and here is where I'll jump to I, how many things are in there on the ith iteration? I minus 1. And how many comparisons do you end up doing? I minus 1 log of I minus 1. That's why we didn't go up here. Right? What is log of 1? Well, 0. Well, log of 2, we're off by 1 here, but it doesn't matter. But it doesn't change that much. It grows very, very slowly. On our last iteration, there are going to be how many elements in there? N minus 1. And consequently, we do log base 2 of n minus 1 comparisons. Right? So how much total work am I doing here? What is the sum of all of these values? Well, first of all, you can kind of ignore this one, right? So we'll start here, right? The size of the heap goes from 1, 2, 3, all the way up to n minus 1. So the size is going to vary from I, running from 1 up to n minus 1. What are you summing each and every single time? You're not summing these, you're summing these. You are summing I minus 1, right? Or if you're going to go from 1 up to n minus 1, let's just simplify it to log base 2, but I'm not going to write that. Why? Because we're computer scientists. All of our logs are base 2 of I. There we go. So I am going from 1, 2, 3. Again, this is log of 1 plus log of 2 plus log of 3 plus dot, 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 plus log of n minus 1. Okay? Now, how can I simplify this? So remember your log identities. Log of a plus log of b is equal to log of ab. Apply that on each and every single one of these, and you'll come up with just a single log of 1 times 2 times 3 times ... times n minus 1. Yep, so what is 1 times 2 times 3 times 4 times 5? What is that? Log of n minus 1 factorial. Good. Now, we're interested in big O analysis here, and I do not like that minus 1 right there. So let's just make it bigger. Right? This is log of n factorial. Right? That's even bigger, right? All right, well, what am I going to do with this factorial here? First of all, factorials are huge. They're super exponential. What happens, though, when you take a logarithm of something that's very large? It becomes more manageable. Not very small, but much, much smaller. So I'm going to show you that this is actually less than or equal to log of n to the n. Why is that? So consider these numbers here. 1 times 2 times 3 times ... all the way up to times n. How can I make each one of those bigger? 1 is less than n, right? Less than or equal to. 2 is less than or equal to n. 3 is less than or equal to n, ... n is less than or equal to n. So if I replace each and every single one of these with n, right, then I'm making it bigger. And if I've got n n's multiplied together, what do I have? N to the n. Now why does that help me? Because I'm going to think of another log identity. Log of a raised to the b. What happens to that b right there? It comes out front. And I am left with n log n. Hey, that looks familiar. That's the best case running time of quicksort. That's the best, worst, and average case time running time of merge sort, right? And a lot of other algorithms that you would apply the master theorem to and get n log n. So this first sequence right here is going to be order n log n. We've matched the best case running time of quicksort. This is average. This is worst case. This is best case, right? Actually, best case can be a little bit better. Right? But in any case, this is the worst case. Right? We've matched the efficiency of quicksort, but we've done it with very, very simple dumb code. Right? Now, we still have to be careful because what about this phase right here, where you're taking stuff out? If I did a full analysis on that, what would it look like? What's the size of the heap when it starts? Well, n, then n minus 1, then n minus 2, ... until you get down to a size of 0. So it's this thing, but in reverse. And we've already done that analysis. That's going to end up being n log n again. And so we have two of these things. We have order n log n. But because these two phases are completely independent, when I add them together, what do I get? 2n log n. But what's the whole point of big O analysis? We forget about those constant order terms sitting out front. And we are left with n log n. So the takeaway on this is that heap sort not only matches the efficiency, but it does it with a very simple, smart data structure. Why it's not used in practice more often, I don't know. Well, because there's this other thing over there called Tim sort that in practice, empirically, it does a little bit better. Right? All right, what I want to do with the rest of our time here, it won't take too long either, right? We might be able to get it done really quick, is let's do a heaps implementation, our own heap implementation. Now, we're not going to do it all. Instead, I'm just going to have an add method here. Let's take it from the top here. I'm keeping it simple. This is going to be a heap of integers. You would not do this in practice. In the practice, you would do a parameterized type so that this heap can hold whatever you want. in which case you would have a comparator like you hopefully did in your list implementation. Private comparator for elements of type T, CMP. That way, when you have two elements and you put one at the bottom and you've got a parent-child relationship here, you would say, are they in order or out of order? CMP, you'd hand that off to CMP and it would return something negative, positive, or 0 depending on the relative ordering of those things. We're going to keep it simple though, right? I've got an array implementation and I've just made it to size 100. I won't worry about resizing either. Right? Those are both things that we've done before. Those are things that you've probably done, hopefully, in your assignment if you chose to do like an array-based list. I will keep track of the size, though. Initially, it's going to be 0, and we're going to have a capacity here for at most 100 things. Now, remember what a heap looks like here. The way that we do this is we burn the first index. Right? So index 0, that'll never actually be used. The root is going to be at 1, 2, 3, 4, ... all the way up to size. So where's the next available slot? If I've got, like, say, 63 stored here in this particular example, 1, 5, 30, ... So where's the next available slot? It's going to be size plus 1. Right? That's where I'm going to put this element in order to simulate it being a new left child of 53. Then I need to go through the process of comparing it and swapping it, comparing it and swapping it until we're done, or until we get up to the end here. Okay? That's the setup. Here's my add method. Right? I've also got a toString method here that will print it out so that we can take a look at it. Note here that it's only going to be printing from index 1 because we burned that first index, at index 0, all the way up to and including the last index. Right? So, for example, it's empty. It's going to print something that's empty. I've got a randomizer here that's going to add 3 random numbers to this, and then we'll test it more rigorously later. Right? So let's outline this first in pseudocode. Right? Let me create a new, come on, just a second. There we go. All right, let's come over here, and let's think about how we would end up adding something. Add, say, x to the heap. ... Right? Let's just outline it in pseudocode, not even formal pseudocode, so pseudocode. Right? What are we going to do first? Well, pictorially, we add it to the end here. Right? So we're going to add x to the end of the array. Okay? 2, we're going to heapify. While x is greater, remember it's a min heap, min heap, so less than its parent, what we're going to do is we're going to swap x and the parent, and then A, B, go to the parent. Again, pictorially, what we're going to do is we're going to compare it with its parent. If this thing is less than its parent, then we need to swap them. Once we've swapped them, I repeat that operation by going up here. Okay? So if I were to insert 42 here, these would end up getting swapped. 42 is now up here, and I need to compare it with its parent. When do I stop? I stop when x is greater than its parent. Right? Because now I know that it's in the proper slot. Or while we are still within the tree. Oops. While we're still within the tree, there we go. It should be right there. While we're still within the tree and x is less than the current parent. Now at the very end, I need to be keeping track of my size, so increment the size. There we go. All right, there's my outline. So I need to find that first available slot. Right? Where's it going to be? So I'm going to place x into the array. array sub something is equal to x. Right? What is that something? Right? So now careful, if there are 5 elements in there, remember we've burned the first index already, 0. So 1, 2, 3, 4, 5. Where do I need to put that new guy? Size plus 1. There we go. In fact, let's save that off into a current index. What we'll do is we'll take that and use current index. Why? Because I'm going to use that current index, and I'm going to go up and up until I get to the root node there. I will start here at my current index, and then I'm going to look at its parent. Right? So while we are still within the tree, and the current index value is greater than the parent value, there we go, then I will, it's not behaving right, but whatever, then I will, you know what, let me put this in the comments here. While we are still within the tree and the current index is greater than the parent's index, then what I'll do is, very Python-y here, what I will do is swap the current index and the parent, and then go to the parent, dot, 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 right? And then at the very end, what was I going to do? I increment the size. I don't even need to put that in pseudocode, this dot size, plus, plus. There we go. All right. Cool. Now let's go ahead and translate that while loop. While. Right? While we're still within the tree. So remember that my current index here is going to be going down, right? It's going to be going from the very bottom here at this size, and then I'm going to back up to the parent. I'm going to back up to the parent. I'm going to back up to the parent. At some point, where do I end up? Right here. So while my current index is 1 or greater, in other words, it's greater than 0, while the current index is greater than 0, there's my first condition. We're still within the tree. Now I need to compare it with the other guy, my parent here, right? Greater than 0, greater than, yeah, that's fine, right? Yep. And this dot array dot current index, right? There I'm going to, is greater than my parent's index. So this dot array of parent. There we go. Then I will need to swap them. Swap, and then go to parent. Right, there we go. So help me out. Wait, current index is less than its parent, right? Then we want to swap them. Because it's a min heap, we want it to go up. So let's change this. Did I write my pseudocode correctly? Is less than. Yep, I did. I just didn't translate it, transcribe it correctly. It's less than its parent. There we go. Okay. What's my parent? I'm at the current index. My left child is going to be 2i, the index is I. My left child is going to be 2i. My right child is going to be 2i plus 1 right next door. How do I reverse that and get back up to my parent? There it is. Remember that if you are at a current index I here, you jump to its left or right using 2i and 2i plus 1. And so reversal here will be dividing by 2. Right? So if I were at, say, index 5 divided by 2, floor, that's going to end up being 2.5. What's the floor of 2.5? 2. Right? If I were at index 6 divided by 2, the floor of that is going to be the floor of 3, but it's already an integer value, so 3. Now, in Java, how can I achieve this floor right here? If I were in Python, in fact, I've got my Python up for another class right next after this one, but if I did something like this in Python, x is equal to 5, y is equal to 2, and z is equal to x divided by y. What value does z have right now in Python? If I were to print z, what would it end up printing? 2.5. Why? Automatic conversions, right? Now, translate this all to Java or C or C# or any statically typed language. There we go. Actually, in Java, it wouldn't work. In Java, it'd probably be a compiler warning, but let's think about C, right? What happens now? So is this 2.5? Nope. What happens? Truncation. It becomes 2. Now, that is not rounding down. That is not actually the floor value. What it's doing is it's taking the fractional value and simply just chopping it off, truncating it off. But in effect, because we're always positive, it's going to have the same effect. We don't have negative index values, so it'll have the same effect. All I'm going to do is say current index divided by 2. Right? Divide by 2, and it truncates automatically. It floors it automatically. Now I need to swap it. So int temp is equal to, actually you Pythoners here, how would you go about doing a basic swap? I've got A and B. How do I swap them? B, A. We don't have that luxury here, sorry. So int temp is equal to whatever is stored in the current index. Then you're free to go ahead and store its parent value into that index and store the temporary variable back into that one. Right? Those coming from a C background, could you do this with a function? Yeah. In Java, can you do this with a function? Nope. There is no pass by reference in Java, so you can't. There's no way that you could write a function to do this with primitive types like integers. Okay. Now what? Go to the parent. So what is the index of the parent again? It's going to be that current index divided by 2. And so current index is equal to current index divided by 2. And since we've got time, right, is there a better way of writing that? Divide equals 2. There we go. Is there another even better way of writing that? If you're always going to divide by 2, have you been exposed to bit twiddling? Right? So current index is equal to current index. If you want to divide it by 2, you can shift it by 1 bit. Right? If you want to multiply it by 2, you can shift it by 1 bit. So let's understand this before we move on here. Right? So if I were in grade school again, right, and you wanted to multiply by 10, 3.14159 times 10, right? Do you really even have to think about it? No, what are you going to do? Take that decimal point and move it over. Right? If you were to multiply by 100, what would you do? You'd move it over by 2. In other words, however many zeros there are here, you're going to shift it to the right or shift it to the left. That dot there, that period, floats to the right or floats to the left. And now you know why we call them floating point numbers. Right? What happens when you do it by values of 2 in a binary system? So let's go ahead and just come up with a number here, I don't know, 13. How do you represent 13 in binary? 1, let's see, 8. So 4, 2, 4, 8. 1, 8, 4, and 1. Okay, 1. There we go. All right, is that right? 1, 4, 5, and yep, that's it. All right, there we go. All right. Now, what if I were to divide it by 2? Remember, with truncation. So divide by 2 would give me what? 6. Well, what if I took this and I floated, there is an invisible period here. What if I floated it over here by 1? What value would that be? 1, 1, 0. Right, that's 0, 2, and 4. So sum all those up and what do you get? Oops. Sum all those up and what do you get? 6. Right. Question? No? Okay. So what would happen if you tried to do it the other way? What if you floated it over by 1? Let's go ahead and get rid of all this. What if I floated it from here over to here? 11010. Right? Now in the binary, this is going to be 1, 2, 4, 8, 16. And so this is 0, so we only take 2, 8, and 16. That's 24, that's 25 in my book. Right? And what is, 26, right? Sorry, I can't do algebra. Thank you. 26. Then that makes more sense now because 13 times 2 is, guess what? 26. 2 plus 8 plus 16 is 26. There we go. So all you have to do is shift it to the left or shift it to the right. And in most programming languages, you can do this. If you've got a number x, you can shift it to the right by k bits. So this is shift x to the right by k bits. And so if it's 1 bit, then that means that you are dividing by 2. If you are shifting it to the left here, you're multiplying by k bits. Right? And it is less than, greater than, greater than. Nearly every single programming language that I know of supports this. Python, C, Java, all included. You can do basic bit twiddling like this. Why would you want to do this? Because then you can do basic bit masking, right? So x, one single ampersand, some hexadecimal number here, A, E, F, 2, or something like that. This is called masking, right? You can get individual bits out of a binary number. And then you can basically encode 32 booleans with one single integer because it's a 32-bit number. A whole bunch of tricks like this in system programming to do everything at the low-level bit level, okay? But that's division by 2. So what we're going to do is we're going to go to the right by 2 to do division. I said that right? Yeah. In any case, I'll go ahead and keep it simple and do that right there. In fact, I'm not going to probably end up posting these, but I'll go ahead and put it in a comment right there. All right. I've already incremented my size here. Let's go ahead and test this with 3 random numbers here. It's going to print every single time, so let's verify that it actually looks like a min heap each and every single time. Right? So initially 67 is in there, and then 94 becomes its left child, 70 becomes its right child. That was really interesting, wasn't it? Right? What is that going to look like? 67. What were the other ones? 94 and 70. Right? That ended up not swapping anything, but at least it worked. Right? Let's go ahead and put in something much larger now. There we go. Oops, no, I don't want that many. Right, there we go. All right. Is that a min heap or not? Let's find out. What I'll do is I'll come over here and resize this so I can see it. There we go. Bring that back over there. There we go. All right. So let's make sure that this works with 10 elements by drawing it out. 4, and then 6, 19, 30, 30. We're allowing duplicates here. Right? 95, 19, allowing duplicates. 61, 69, and 41. Does that look like a min heap to you? Yeah. Is it sorted though? No, because that's not what a heap is. Okay. We're not going to do it because we don't have enough time, but what's the other method? Get and remove min. So public int get min or remove min. Let's just call it remove min. Remove min. So what would that look like? We can do a little bit of it, right? Int result is equal to, what is the root value of this? This dot array sub 0. Remember that we're birding that first one, so it should be 1. And ultimately, we're going to return the result after we've heapified it and fixed it and consequently taken it out, size minus minus. Right? I can do maybe half of it already without really even thinking here. Right? So what's the next step? I would swap the last element and the root. So, actually, what I wouldn't even swap. I would promote the last element to the root because I've already saved off the root in this result right here. So this dot array of 1 is now equal to the last element. Where is the last element? If there are 5 things in there, 1, 2, 3, 4, 5. This dot array of this dot size. Why not minus 1? Because remember that we're burning that first index there. There it is. Now, to do, heapify the root value, so int current index, will end up being starting at 1 here. Heapify the root value down the heap until either 1, the heap property is satisfied, or the current index is beyond this heap. Right? So set up a while loop there, and I'll let you do it yourselves. The only trick here would be looking at its 2 children. Which one do I swap it with? I would need to determine that the left child is the minimum or the right child is the minimum. Then you've got some corner cases. Is the left child and the right child, do they exist? So you've got some a little more work here than just that we did up here. Because it's actual code, it's an actual implementation. If the left child exists and it's less than the right child, if the right child exists and it's less than the left child, then that determines which one you actually compare it to. Once you've made that, then it's pretty straightforward. If this is greater than that, then you swap them and move down there. And you keep going until you've fallen off the edge of the tree. Right? So I'll leave this as a to-do. Okay. Any questions? Any homework questions? No? All right. Remember, no lab this week. Instead, they will be there, of course, in the regular lab session so that you can go ahead and go at any time and get some help, ask some questions, review anything that you've missed or anything like that. But otherwise, on Wednesday, we'll do a quick retrospective of the course and nothing on Friday. Have a good one.
Thank you for the class, man.
Sure, no problem.
Really fun one.